Okay, this is the last part of just like the probability stuff that I'm going to cover so far. This is probably the most equation heavy, but this is the one that will help us figure out a lot of our probabilities instead of just focusing on just singular events. And this is talking about and, or, and complement. Now, prior to that, we were learning about independent and dependent events, um, where independent events is where event A is not affected by event B, while dependent event A is affected by another event we call B. So let's figure this out. So when I'm trying to figure out more like probabilities that involve multiple events, sometimes it can be a combination of the both, or it can be like I can have either or. And this is the idea of, let's say for example, like I had poker. For poker, let's say I had a straight. So basically, like let's say I had two cards so far. I have like a 9 and a 10. Basically, for poker, the way that it works is that for me to get a good straight, especially like a royal straight, I want a jack and a queen and a king, right? All of these contribute to me winning a good straight. I mean, obviously it's not the best hand, but hey, a straight is a straight. This is why this is going to be an example of and. So this is going to be the and, because I want the jack and the queen and the king. So notice that I'm using the word and. So with this is an example of the and probability. So let's think about that. Chances of me, if I think about it, getting a jack, a queen, and a king all at once is probably really rare. And so if I think about this for the and probability, what I'm going to do is that I'm going to think about it like this, where because they're different events, and it's going to be like even more, like you have one probability of one event, and it gets even more worse after the other, chances are that the and probability is going to be multiplying the two. Let's consider like the example of flipping two coins. And then heads on both. So with this one, for the first one getting heads, it's head on one, and notice I'm going to put and head on two. With this one, I'm going to do 1/2 times 1/2 to give me 1/4. And we can see that with the probability tree. So we can see with the probability tree, for the first coin, we have heads and tails. That branches off to the second coin, also getting heads and tails. Notice getting heads on both would just be one of the branches, which makes it sense to be 1 out of 4. So we already touched up a little bit on like what and can look like based on a probability tree. Okay, so what does this mean for the and probability? So I'm going to talk about event A and event B. Basically, the probability of both of them happening can be two things. It can be 0 or probability of A times the probability of B. Now, it's only 0 if A and B are dependent. While this one is going to be independent. So let's give an example of when it's 0. Basically, let's say that the probability of A and B can be basically, let's say me rolling a 1 and a 2 on the dice. And I'm going to say that this is going to happen one time. Well, that doesn't really make sense, right? Because when I think about that, I can't have both of them happen at the same time. And because of that, that's going to be 0, right? I can only roll one value on the dice. So let's consider then this idea of or. So for or, for A or B, Notice how for and, we focus on multiplication. So what I'm going to define or is that's going to be addition. Because or is basically combining the two probabilities. But then I'm going to subtract in case if they are independent, the differences between the both of it happening. I'll later discuss this in a different problem, and we'll have plenty of practice with or. But this is basically the general way that we define or. The last one is going to be complement, which is basically the opposite of an event. So basically, if I have like event A being like rolling a 3 on a dice, the complement of that would be not rolling a 3. So I'm going to say the probability of not A is going to be 1 minus the probability of A. 1 represents the total outcomes, the total probability space. So like all the possible outcomes, and then probability of A is the probability of A. I already made some examples, so let's go over them. So it says a single card is drawn from a well-shuffled deck of 52 cards. Find the probability that the card is a club or a face card. So notice that what word am I using, right? Notice how it says or. Because I'm using the word or, basically what I'm going to do is that I'm going to create that equation. I'm going to let A, so notice I'm going to label my events, that the card is a club. And then B, the card is a face card. So if I write down the probability of A or B, so I'm going to write down A or B, that's going to equal to the sum of both minus the probability of A and B. So we'll get a little bit of touching of or and or. Let's figure out the probability of me getting A. The card is a club. In a deck, there are 4 suits. There are hearts, diamonds, clubs, and spades. So I know that the card being a club will have 13 cards because I divide it into 4s. So since there's 4 suits, it's also just 1/4. The probability of it being a face card, this one's a little bit trickier, but basically since there are 4 suits, if it has a face card, there's only 3 face cards. There's a jack, a king, queen, and a king. So what I'm going to do is I'm going to multiply this 4 times this 3. So I'm going to get 12 out of 52. So I basically have almost everything to combine that with. But then there's one last one. So I'm going to find out the probability of A and B happening. So is there a chance that it could be a face card and a club? The answer is yes, right? It's going to be 3 out of 52. It's because I can have a jack, king, and queen. That's also a club. I can have a jack of clubs, queen of club, and king of club, right? So then what I have to do is I have to combine all these 3, right? The probability of me getting A or B would equal to 13 out of 52 plus 12 out of 52 minus 3 out of 52. So notice what I did with probability of A and B. I figured out all the combinations that I can have for either or. Sometimes it's going to be 0, as I said here. Sometimes it could be independent, and you can see that for probability A and B, it is a little bit different there. But these are basically the 2 ways that we can define it. So for this case, it wasn't really like I multiplied like those 2 together, like the club times the probability of face cards, right? I didn't multiply them. But what I did was that I figured out what is like that possible outcome where they both share it. This one requires, I feel like, the probability of A and B a little bit more thought into it. So let's figure this out. I'm going to actually change this definition to not just be 0, but 0 or another probability. So it's going to be another probability depending on what we have. Okay, so what I'm going to do is I'm just going to calculate this. So then 13 plus 12 minus 3, that gives me 22 out of 52. That's the probability of getting a club or a face card. All right, moving on. This is another or, right? Experiment consists of tossing a coin, then rolling a die. Notice how it says then, so we're doing the first event as tossing a coin, then we roll the dice. Find the probability the coin lets heads up, or the number is 5. So again, let's label our events. This is going to be an or problem. So I'm going to label that. So the A is going to be coin gets heads. And then B, the dice is 5. Again, what are we going to do? So in this case, we had to figure out the probabilities of these first off, right? Probability of A, well, the coin getting heads is 1 out of 2. And the probability of B, the dice is 5, would be 1 out of 6. Okay, so now we had to figure out the probability of A and B happening. So can the coin get heads and the dice getting 5? Yes, they both can happen at the same time. So that means that these are basically independent events, right? Getting heads does not affect getting the dice is 5. So what I'm going to do is I'm going to say that probability of A and B is going to be the multiplying those two probabilities onto itself. So 1 half times 1/6 is equal to 1/12. Okay, and then with that, basically what we're going to do is that we're going to combine all this stuff. So writing the equation again, probability of A or B gives me probability of A plus the probability of B minus the probability of A and B. This is going to be 1 half plus 1/6 minus 1/12. I'm going to make them all into the denominator 12, so 6/12 plus 2/12 minus 1/12 is equal to 7/12. So I'll go over this problem again because I did went a little bit fast. Tossing a coin, then rolling a dice. So, and then I notice I have to do or. So I'm going to find out A or B. So I had to label what is my A, what is my B. A is coins getting heads. B is getting the dice is 5. I calculate those separate probabilities. But then I know in my equation I have to get A and B, right? So this is what this is. And then because of that, A and B are independent events. I can roll heads and I can still get dice as being 5. So I'm going to multiply those probabilities together. Therefore, I get that. This is the last problem I'm going to talk about. And then this is probably probably the hardest one. But this is the one that's most relevant. A multiple choice consists of 6 questions. Each question has 4 choices for answers, one of which is correct. A student guesses on all 6 questions. So what is the probability of he gets at least one answer correct? This one's a little bit of a hard question, but I'm going to break it down. So let's say that in the 6 questions, so let's say at least one. So if I define at least one, that means he gets either 1 correct, he gets 2 correct, 3, 4, 5, or 6 correct, right? So we can find out all the probabilities of the student getting that, but that would be doing every single one, right? That gets a little complicated. So basically, instead of us just finding out the probability of them getting 1 correct, then 2 correct, then 3 correct, 4 correct, 5 correct, and 6 correct, what we're actually going to do, and actually if we did this is an example of or probability. But what I'm going to do instead is I'm going to do the idea of complement. So complement basically means that I can do the opposite of what I'm asking for. I asked to get from 1 through 6, but what's the opposite of getting at least one answer correct? Well, the answer to that is none of them are correct. So the way I'm going to write this question, this then, is the probability of at least one is going to be equal to the probability, I'm going to say 1, sorry, 1 minus the probability that none are correct. So basically, let's think of it like this, right? If there is an answer choice of A, B, C, or D, let's say that B is the correct one. If the first one is not correct, that means that he either chose A, C, or D, right? So this is about the first question. So the probability that the person got the first one incorrect, well, that's 3 out of 4, right? Which makes sense. I have 3 options that are not correct. So I'm going to say they are incorrect. And then the 4 represents the choices. What about the second one? Well, the second one, if they didn't get incorrect, that means they also get 3 out of 4. Well, that happens throughout all the 6 problems, right? So basically, notice what I'm going to say for none are correct. So if I write none are correct, that's basically me saying that the first one is incorrect. It's not, and then I have to figure out if it's going to be and or. I can't have this because if I have the first one being incorrect or the second one incorrect, well, that means that it's not going to be none of them are correct, right? Because I have to have both of them be incorrect in order for me to make this claim. Same thing if I had the third one incorrect, and the fourth one incorrect, and the fifth one incorrect, and the sixth one being incorrect. So with that, we're going to use the and probability. So and probability for all the questions. But luckily, they're all the same probability. So I'm going to say the probability that 0 are correct is going to equal to, well, 3/4 times 3/4 times 3/4 times 3/4 times 3/4 times 3/4. So each of them is a question. So that's the probability of none of them being correct. But remember, I'm trying to find out at least one. So what that means is that I have to subtract this. I'm going to make this into an exponent. This is 6 of them, so I'm going to say 1 minus 3 to the 4th, 3 over 4 to the power of 6. If I use a calculator for this, let's see what we get. So I'm going to calculate in my thing 0.75. I'm going to raise this to the power of 6. And I'm going to say minus 1. So this is going to be around 0.822. So he has a pretty good chance of at least one of them getting correct. So this is basically what we do for probability, right? We have to find out, in this case, at least the complement where none of them are correct, which uses the idea of like the and probability. And notice how for the and probability, we're going to be independent. Because, right, I can get the first one being incorrect and the second one being incorrect, and they don't affect each other, right? So this is the idea of the 3 things, right? It's going to be and, which is going to be mainly this multiplying probability of A times B. If it's going to be independent of one another, it's going to be dependent, it's going to be 0 or another probability. If I did or is basically this main equation. I'm going to box this one too. But the probability of or is just adding the 2 and then subtracting the and probability, while the complement is basically for not A, probability of 1 minus probability of A. So these are the three ways that we can calculate probabilities based on multiple events. I know the last one was a pretty hard one. You can see that I wrote like a lot of things, but we'll kind of go through these problems one by one, more and more throughout class. But that's basically it. I think next we're going to be talking about conditional probability. So with that, we're going to end.